Okay, off we go. So here's where we were last time. We were talking about optimization, and roughly speaking, our strategy for finding interior critical points is a lot like it was in single variable calculus. So just a quick rewind. Here's what we did in single variable calculus. We observed that if certain conditions are satisfied, then the function, one way or the other, possibly to the left, possibly to the right, but one way or the other, the function is still getting bigger, and if it's still getting bigger, then it's definitely not a maximizer. And so that eliminates almost every point in the domain, and all we actually then have to do is look at points where one of those conditions fails. Any one of these conditions fails, well, these are the points that we can't eliminate, and we have to consider them. We'll give them a name. We call them critical points. That's just a label that says, yeah, we have no idea what's going on there. Right? This might be the point we're looking for. Can't eliminate it. Okay. So we call them critical points. We check them. So same thing here. Again, here's a list of conditions that allows us to conclude that a point is in some direction or another still increasing. Couldn't therefore possibly be a maximizer or minimizer. And so all we have to do, again, is just look for points where one of these conditions fails. Who knows? It could be any one of the three. If any one of these three conditions fails, then again, I can't eliminate those points as possible maximizer, minimizer, whichever one you're interested in. And so we call them critical points, and we check them. Okay. All right. So let's see. You know what? Before we go on to an actual algebraic example, let's talk about what these critical points might look like. And looking at this picture I have drawn here, I mean, what you're kind of expecting is the local max, right? The little mountaintop, right? Little hilltop, whatever. But there are other possibilities, and when you have two independent variables, there's a little bit more room to move around and for different weird things to happen. And so you get kinds of critical points that literally there is no analog in single variable. And so in particular, I'm thinking about saddle points. So a point like this where it's sort of concave up in one direction, sort of concave down in the other direction. And again, that's kind of weird, and there is no single variable version of this. So that's a possibility. And it gets weirder. There are other possibilities for what a critical point might actually look like. And one of them is called the monkey saddle, which I think is weird and also kind of funny, because you've got to imagine there's some little monkey sitting here, and the monkey has one leg there and one leg there, and then his tail is hanging off in the back, right? So it's kind of funny, and you can do a Google image search, and there's some, adorable little pictures of monkeys on saddles and that kind of thing. But if you think about it, it's kind of a weird shape, and again, there is no single variable version of this. So again, it's kind of curving downward in three different directions now, at the same time kind of curving upward in three different directions in between them, right? So very strange, and you can let your imagination go wild and try to visualize other kinds of critical points and what might they look like, right? And here's an interesting one, what I like to call a shoulder, right? So I'm going to use my own shoulder as a visual aid. So inflection point in this direction, but concave down in that direction. Right? So again, that's not a thing in single variable, right? There's not enough room we don't have multiple directions in the domain to have weird stuff like this happen. Okay. All right. So, moving along, let's do an example. Let's see here. Here we go. We want to find the critical points of this function. Now, this function is defined everywhere, so every point's in the interior. There are no non-interior points to worry about, so easy to check that first condition. Reminder, keep in mind, we're checking these three conditions right here. looking for boundary points, we're looking for differentiability failures, and we're looking for where the gradient's 0. Okay, so there are no boundary points. There are no failures of differentiability. This is a polynomial. It's differentiable everywhere. Cool. Easy to do. And that leaves us the third condition to check. We take the gradient. We ask, where is that gradient equal to 0? And you do the ensuing algebra. Now, this is an easy example. This is a deliberately easy starter example, so we don't get bogged down in algebraic challenges. But solving really just means literally solve for x and y. Now, y is ultra easy to solve for. And x, not so bad, really. Don't do too fast and loose on this. Don't forget the plus or minus. A lot of students surprisingly often mess that up, and it matters, right? Because we now have 2 critical points, not just the 1. Okay. All right. So now, so I say this was an easy one with the algebra. What would harder algebra look like? Here is some harder algebra. Here we have an example where, we have a system. And by the way, this isn't actually a gradient, but the point to this example is to see how this kind of algebra can actually be a little bit more challenging. So, you see that this has kind of got mixed equations. It's not like there's an x equation in which to solve for x and a y equation in which to solve for y. Wouldn't that be nice? No such luck. So here's what we do. We look at this first equation. Not hard to conclude that x squared has to equal to y squared. And here's the problem. That leads to 2 possible cases. X could equal to y. X could equal to negative y. And this is what I'm going to call a landmine. A lot of students mess this up. A lot of students, I suspect, bad high school decisions. But anyway, a lot of students will take x squared equals y and will conclude that x equals y, and will kind of sweep this under the rug like, come on, whatever, who cares? What's the big deal? All right. This is a tragic mistake. Tragic mistake. For one thing, it's not mathematically legitimate, right? There's a little minor point there, okay? So again, what we're doing here in this course, we're not here to find answers. We're here to do valid mathematical reasoning, right? So, really big point then, actually, that is not mathematically valid. The other problem is that sometimes, and this is a good example, this case will actually lead to critical points that you would otherwise have missed. Right? And, again, kind of a big deal. Right? So, please do be really, really careful with your algebra. In fact, you're going to find that today that's going to be one of my big themes. Is be really, really careful with your algebra. There are a lot of, sort of standard algebraic blunders that are easy to make if you're not careful. And, you gotta tighten up the system so that you don't, make any of those blunders. Okay. All right, so there's 2 possibilities. We don't know which one's going to be the case. Could be either. And so we have to actually entertain 2 separate cases. So we will start with this one. Call this case 1. If it should be that x is equal to y. Then what can we conclude from that? Okay, well, if x is equal to y, I can take that and plug it into this second equation. This second equation then turns into this. And this equation, looking at the sort of the last part of it anyway, I can, no big deal, solve for y. And once I know y, you got to be careful about this. Once you know y, the assumption of your case also allows you to conclude x, right? So the y coordinates of these 2 critical points I just found, we got from that equation. The x coordinates I got from plugging back into the case. Everybody happy? Okay. All right, now again, if you stop there, problems already complained about, so I won't repeat. But let's consider the second case now. Again, just as possible, right? And if x is equal to negative y, you take that and plug it into here and see what that turns into. That then turns into a slightly different equation. Right? Slightly different equation. And when you solve this slightly different equation, you get, notice, different values of y. At least one of them is a different value of y that you would have missed otherwise. And not only is it a different value of y, even if it had been a value of y you'd found before, we're going to take those y values and we're plugging back into a different case. Right? And so we can get not all the same critical points. Now, okay, sure. One of them we already had. Sure, fine, right? So that's not news. No problem. We can't eliminate that point twice, right? So whatever that means. But notice, importantly, we do get a critical point that we otherwise would have missed. So, very important. You've got to be careful with that algebra. Don't play too fast and loose with your algebra. Let me pause. How are we doing? Is everybody okay? Questions? All right, so moving along. Second derivative test. Y'all remember the single variable second derivative test? The big idea is this second order Taylor polynomial. And we talked about Taylor polynomials last time, I guess it must have been. And the way the second derivative test works is to say that, look, it all basically comes down to this second order term, and 1/2 is definitely positive. And let's see, x minus a quantity squared is definitely positive. I mean, other than at the point x equals a, and we're trying to figure out what happens near, not at. So that's definitely positive. And so if I want to know if this curves upward or downward, I just have to look at the second derivative. Simple as that. If it's positive, it curves up, and you have a minimum. If it's negative, it curves down, and you have a maximum. Old news. Right? But again, it all comes down to that second derivative because of the Taylor polynomial. Okay, so in multivariable, per section 4.1, there's our Taylor. Right? Second order Taylor polynomial. And in the same way, it's all going to come down to whether this second order term is always positive, in which case we have a minimum, or always negative, in which case we have a maximum, or, it's also possible it could be neither, or it's also possible that we can't tell, right? So there's various different disappointments that we might have to deal with. But anyway, that's the question. And you'll notice it's no longer as simple as, well, just look at the factors, because we have some funky algebraic operations going on here. This is not a multiplication of scalars. Here we have a dot product. Here we have a matrix vector product. I can't just look and decide what's positive, what's negative. And y'all will recall long ago, but nevertheless, you'll recall that deciding on whether a quadratic form is positive or negative definite is a whole process. And that was a linear algebra, 218 or 221, whatever, thing. All right. So it turns out, because the matrices in question are symmetric, that there's some cool linear algebra you can do. That's not what this class is about. This is a little heftier. Notice I've got this labeled as optional. Little bit of, it'd be a digression that we just don't have time for and doesn't quite, again, meet the bar of what we need to talk about in this class. But it is some pretty cool linear algebra, and if you're curious, this is kind of an outline, just hitting some, landmark points along the way, and feel free to try to fill in the gaps if you're looking for a linear algebra challenge. And the punchline is as follows, and this is what you do need to know, is this what we call the second derivative test. This is only for functions of two variables. It's harder to write down if you have three. We're only going to do this for two variables. And here's the test. It's a little weirder than the single variable. In single variable, there's 3 cases. Look at the second derivative. Positive, negative, 0. That's it. Whole story. Right? Here it's a little bit weirder. The first thing we have to do is look at the determinant of that second derivative matrix, the Hessian matrix. And each of those possibilities, positive, negative, or 0, gives kind of 3 separate, what you might call sub-tests. And the first one is the easy one. If that determinant is positive, then roughly speaking, we have something that's going to be kind of like the single variable second derivative test. You look at an individual second derivative. You can use fxx or fyy. It's got to be one of the diagonal second derivatives. It can't be a mixed second derivative. It's got to be either xx or yy. Positive implies a minimum. Negative implies a maximum, just like in single variable, right? So this is what I'm going to call the good news case. This is the familiar, okay, seems like what we would have expected, case. So, here's the thing though, again, there are 3 cases here. If this Hessian determinant is negative, then forget about looking at fxx by itself. It doesn't mean anything relevant to this case. If that determinant's negative, you have a saddle point of some description. Might be a monkey saddle, I don't know. But it's a saddle point of some description. Okay. And then there's the third case, and again, not the craziest thing you've ever seen. This is the case where, again, the test fails. It doesn't mean that you don't have a maximum. It doesn't mean that you do have a maximum. It doesn't mean anything in terms of a conclusion. It means that you cannot draw a conclusion based on what we're seeing from this test. So you just have to kind of throw up your hands and say, well, I don't know. Okay, and again, there is a version of that in single variable. Okay, so this is a pretty straight read. I'm going to hit some real quick highlights, but I'm going to go back to that previous example. We looked at this function. We found these critical points, and now with our new second derivative test, let's classify them. And so we compute the Hessian. Right, there's the determinant of the Hessian, little algebra. Y'all can do that. And then you plug into the test. So let's see here. I will do like so I can point at this first critical point. The determinant's negative. That means saddle point. Just following the little chart there. Okay. Looking at the second point there. Plug in. That Hessian determinant's positive. Okay. Yeah, that means I have to go further. Okay, this, apparently I need to look at fxx. Fxx, of course, is that right there. When you look at that value, do you get positive or negative? Well, we get positive. Positive means local min. So just like I say, it's very follow the algorithm. Y'all are good at that kind of stuff, I'm sure. Very straight read. Fill in the details that I kind of glossed over, but that's the big idea of how to actually put this into action. What do you think? Does everybody see the big picture there? Think y'all can do that? Okay. All right. So yeah, there's some different questions we're going to ask. What we've been doing so far is looking for critical points, but more to the point, we've been looking for interior critical points. We're not on the boundary. We're not confined to some surface. No constraints. Just here I am. I'm free to move in whatever direction I want to move, and let's just go, try to find critical points in that scenario. So there are nastier questions, which is, what if you have a boundary, right? And how does that change the question of how you find maxes? And this is a really important theorem here, that there are various ways that, in fact, there might not be a maximum to find. And this happens sometimes. So for example, let's look at this scenario right here. You notice that this domain, the interval on the x-axis there is open on the left. And you look at the little graph there, that graph just keeps getting bigger and bigger and bigger as you approach that sort of non-existent boundary point, right? There is no endpoint. That's part of the domain anyway. And so there is no maximizer to find. That function doesn't have any maximum value. Does that make sense? Everybody on board? Likewise here, now for a different reason, it's unbounded, right? It doesn't have a right endpoint that we just don't include as part of the set. It's that there is no sort of ending on the right. Well, again, the function can just keep getting bigger and bigger. And then likewise, if you have a discontinuity in the middle, and again, that allows you to have an asymptote or something like that. Okay, so the big theorem is, roughly speaking, that these are the only three kinds of scenarios that can make things go wrong. And it's actually surprisingly not that hard of a theorem to prove. It's a little bit beyond what the effort to return ratio is just a little too high, I think, for this class. But it's not the worst thing in the world to prove this. And here's the nice result. If you have these three conditions here, if the domain is closed and bounded, and if the function in question is continuous, if none of these three things happens, in other words, then there is a global max to be found somewhere in that domain. No funny business. Okay. All right. Good thing to know. Good to know when you're not on a wild goose chase. So, this brings up an ugly question, and that is, okay, so it's possible that if our set has boundary points, it's possible the maximizer is on the boundary. How would we find a maximizer on the boundary? How would we find such candidates? How would we identify critical points on the boundary? And it is a completely different deal. The gradient does not have to be 0 on the boundary, right? That's in the interior. So here is a way that you can approach problems like this. Now, here's good news, and I'm not going to go into super detailed discussion of this example because we have a better method that's going to come up momentarily here. But if you don't want to use the better method, which weird, but whatever, on the boundary. Let's look at this top edge. I can analyze what's going on just on that top edge with single variable calculus. Because I can rewrite the function. The function on that top edge is basically a single variable function. You give me a value of x, well, then it follows what y has to be. I mean, we say we're looking at points on that top edge. For any given x, there's only one y. And then you take that x and that y, and boom, there's the value of the function. So it's effectively single variable. X is the input, and f is the output. So in this case, it simplifies like so, and single variable calculus. Take the derivative, set it equal to 0, blah, blah, blah. Now, there's a lot of blah, blah, blah. And it's a little tedious. And all else being equal, I prefer not to have to do that. But you could do that. And the punchline is that you end up with 6 boundary critical points to check. All right, now y'all can read this at your leisure if you're interested. You don't have to. Again, because there's a better method. And here is this better method. This is the way to go if you have a constrained optimization problem. In other words, you're looking on, either a boundary or for whatever reason looking on a surface, what have you. Okay, so I'm going to start with an example of the kind of question that we're interested in. This is what we call a constrained optimization problem. We have a curve in the plane. And among those points, I would like to know which one is closest to the origin. Now, let me start with the silly wrong answer to this question. The silly wrong answer is to say, closest to the origin, I want to make distance as small as possible. How about 0? I think 0 is the smallest possible distance. So I think the answer is that the origin is the point that's closest to the origin. Now that's ridiculous, of course. That wasn't the question. The question said specifically, just among those green points. The origin is not allowed to play. Right? Just among the points on that curve, of those, which one is the closest to the origin? So this is actually a pretty sophisticated, non-trivial question. Right? And so this is the kind of thing that I'm talking about. This is what we're dealing with. By the way, what does this look like? Let's draw a quick picture. So this curve here is some sort of an ellipse. I think it's something kind of like that. And of all of those, we want to find the one closest to the origin, right? So maybe it's like a point here, and that makes that distance as small as possible, right? And probably symmetrically, likewise, that one, right? But we're trying to eliminate like points like that, right, where that distance is clearly bigger. And we want, among the green points, which one makes that distance as small as possible. Okay, alrighty. So some important language that we have to establish just so we can have an easier way to talk about all this stuff. We're going to talk about something called the objective function. The objective function is the function that you want to optimize. In this case, we want closest to the origin, so we're minimizing the distance to the origin. Now, I am quite aware that this is not distance. Right? This is the square of the distance. So very often there are some little fast ones that are kind of cool to pull, and I encourage pulling fast ones when it will make your life easier. The fast one that I'm pulling here is that if I minimize distance, I am also minimizing distance squared. Think about that for a second. If you have 2 points and one of them has a shorter distance, it's also got a less distance squared. This is kind of 2 different ways of saying the same thing. I don't really care that squaring the distance sort of distorts that value. I'm just looking to minimize something, and so as long as what I do to my objective doesn't change where the minimum is, yeah, it's all good. Go ahead. So, a handy little trick there. Okay. Next thing we have to talk about is the constraint function. So the constraint function is the representation of the fact that I am constrained to only look at certain points. I can't just, like in this case, pick the origin. Doesn't count. It's not in the domain. It's not allowed to play. Okay, so the constraint function, very importantly, is a function for which a level set gives the constraint. Right? So the constraint function in this case is this thing right here, sort of the left side of that equation. Now, y level set, arbitrary, seeming, why can't we say the function is graph we're looking at or something like that? There are different ways that you could approach a problem. It's going to turn out to be extremely useful. In this case, extremely useful to think of the constraint in terms of level sets. So if you want to apply this method called Lagrange multipliers that we're about to see, you gotta rewrite your constraint as a level set. And whatever you're talking about a level set of, that is your constraint function. Okay. All right, now before we talk about why that is useful and how does that work and what is this method that we're building up to, let's see a couple of examples just to see how stuff fits in. This question right here, y'all may have seen questions kind of like this even in a single variable calculus class. You want to make the biggest possible rectangular box with the, but the thing is, we only have so much cardboard. We have to pay for the cardboard, right? And the bosses have told us that we only get to use a certain amount of cardboard. Okay. All right. So the thing that we're trying to maximize here, let me leave this highlighted. The thing we're trying to maximize, right, optimize, is volume. So in this example, volume is our objective function. The thing that that describes our constraint, the thing that is fixed, and again, keep in mind, we have to write this in terms of a level set. We have to write this in terms of some function that's not allowed to change. That, our constraint function, is area. All right, so we've taken a question, and we've kind of parsed it in such a way that we have a well-identified objective function and a well-identified constraint function. How are we doing on that? Everybody on board? Okay, so likewise, if I have a limited budget, then whatever my budget is, that's my constraint function, because that's the thing that has to be fixed, as I have a fixed amount of money, right? The budget itself, whatever my spending cap is, that's my constraint. Let's see, what am I trying to optimize? I'm trying to optimize, here we go. We're trying to maximize productivity. Now, I just made this up, right? Just example. If you're running a small business or something, right? Then again, constrained optimization problem. So, I think it's worth noting that, look at these two examples and you notice that these are not abstruse kind of weird mathematical constructions, mathematicians solving problems that they made up for themselves for no apparent reason. This is very real world, right? It's very applicable, very broad, right? There's just a bazillion of these kinds of questions out there in dealing with practical real world stuff. Okay. All right, so here's how it works. This is the cool idea. We have another elimination. 3 certain conditions. If these 3 conditions are all satisfied, there's no way that could possibly be a maximizer. Just no way. Okay, so let's walk through these conditions real quick. The big idea, of course, is that I have some constraint set. The constraint set is described by some equation. In particular, it's a level set, as discussed, right? And let's see here. Now, we have to write down that we need the functions in question to be differentiable, because we're going to do some calculus with these functions, and calculus only works, right, if the functions are differentiable. So, okay, sure, fine. Now let's think about the gradient, what we call the constraint gradient, the gradient of the constraint function. I'm going to suppose that is non-zero. That's the scenario I want to consider, right? Non-zero constraint function. Why do we want it to be non-zero? Well, if it's non-zero, then I can reasonably look at all multiples of it. The collection of all multiples will define that entire line perpendicular to the constraint set. Keep in mind that gradients are always perpendicular to level sets. Right? That's why this is the key point of why we always write our constraints as level sets. Because then I can just look at the constraint gradient and boom, I have a line perpendicular to our surface. Okay, fine. And then what? Well, if my objective gradient is not on that orange line, then it kind of has to be pointing off axis. If it's pointing off axis, then it has a shadow on the tangent plane. And if it has that shadow on the tangent plane, and if I think about, looking at that dot product to compute the directional derivative, how fast is the function changing as I move in that V Direction, well, that's clearly an acute angle, and this is a positive directional derivative. The function's still getting bigger. It's still growing. How could it possibly be a maximizer if the function's still getting bigger? So again, little elimination there. And just like in single variable, just like in the unconstrained case, if any one of these fails, doesn't matter which one, doesn't need to be more than one. If any one of these conditions fails, then, well, then our elimination argument goes away. I have no idea what's going on, and I have to just call it a critical point, and okay, I guess I'll come back and check it later. And the good news is the great majority of points in the domain will be eliminated, and typically anyway, only a handful will come up as critical points. Okay, so that's the method. That's how it works. It's all algebra from here. Now there are some sticky points in the algebra, and I do want to focus on those sticky points. We've only got a few minutes left. By the way, we're going to be doing course evals right after. For the last, let's see here. Class ends at 11:10. So I've got several more minutes here. So here we go, constrained optimization problem. We're looking at a level set of this function, so there's my constraint function. I'm looking for the highest point. Highest point means that I want to make z as big as possible. So z is the thing I'm trying to maximize. And now we play the game. We got f and g identified. I need to look for differentiability failures. I need to look for where the constraint gradient might be 0. And then I need to write down this weird equation right here. This, I need the one gradient to be a multiple of the other gradient. We'll deal with that when we get to it. So, okay, no big deal. These two functions, polynomials, both differentiable. So, we've checked that differentiability condition. Now, let me address a very common mistake that a lot of students make. A lot of students will look at this and say, well, that was a waste of time. It didn't yield any critical points, so why do we even have to do it? And the answer is, well, you have to do it because if you want to claim that you have found all the critical points, you actually have to check everywhere. Right? So if I were looking for a, if I were looking for a football somewhere in this room, right? And if I check the trash can, and there is no football in the trash can. True, I didn't find it there, but I can now claim, yeah, but I know for a fact it's not in the trash can, right? And then when I look other places, right? When I'm done, I can say I literally checked everywhere in the room. Right? If you don't check, then you can't say that you did. So it's actually really important. And again, for mathematical purposes, you got to write this down. I know it's easy. That's a good thing, right? That's not an argument for why you shouldn't do it. That's an argument for why you should do it. Just look at the functions. Usually functions that we deal with on a day-to-day basis are usually kind of obviously differentiable, like polynomials. Boom, write it down. That might be of 1 or 2 points of partial credit right there. Right? Don't leave the money on the table. Get those partial credit points. Okay. Okay, next. We've got to look for where the constraint gradient might be 0. Okay, so we compute the constraint gradient. There it is. Rewrite it like so for convenience. Check to see if it might be 0 by looking at this equation, and linear algebra shows up again, right? We have a little matrix equation, system of equations, however you want to say it. Make sure you remember how to do these. All right, I know it was a while ago, but that's how prerequisites work. They come up, right? So in this case, it's pretty easy to notice that the determinant's non-zero. That means that it's a non-singular matrix. That means that, the solutions are unique. And since x equals 0 obviously works and is a solution, it is therefore the only solution. And it feels like we have found a critical point. And this is a process you have to go through, and it's good that we got to this point. Now, as it turns out, though, also not a critical point. Well, why is it not a critical point? Well, keep in mind what a critical point is a point on the domain that I can't eliminate, right? I'm looking for points I can't eliminate. I don't need to eliminate x equals 0. X equals 0 is not even a candidate in the first place. Right? If I wanted to identify who's the tallest person in this room, I don't need to check for the possibility that my brother might be the tallest person in this room, because he's not in the room. Right? So, silly to entertain this as anything other than irrelevant. Okay. How are we doing on that point? That was one that confused me a lot when I was y'all's age. Everybody good? So the conclusion here is not that x equals 0 is a critical point. The conclusion is that none of the points on the constraint set are what we call degenerate critical points, per this condition. A little bit of lingo coming back to here. This is sometimes called the differentiability condition. This that we just checked is sometimes called the degeneracy condition for reasons that are very mathematically appropriate and have nothing to do with this course. So you're going to hear me say degeneracy here or there. Okay, lastly, we got to look at this oddball little vector equation. So we look at these two gradients. Here's our objective gradient. Here is our constraint gradient, and saying that the one is a multiple of the other gives us that. It gives us those three equations. And now, of course, the only reason we care about those is because we're trying to eliminate points on the constraint set. So I'm going to add in the constraint as another condition, because if you find a point that's not on the constraint set, again, who cares? Right? Irrelevant. I don't need to eliminate it. It wasn't a candidate in the first place. So altogether then, what I have is a little 4-equation system that we need to solve. And this algebra can get a little annoying here and there. Okay, so how to solve this? There are different things to do. Now what you're going to want to do is look at these two equations, cancel the lambdas, and rewrite like this. Very tempting. Very tempting. Here's the thing. You can't cancel 0. Right? If lambda were 0, there would be no reason that those other expressions would also have to be 0. All we need is the product to be 0. If lambda is 0, we just wouldn't be able to draw this conclusion at all. Right? So if we want to be able to do that, we do have to first establish that lambda is not 0. And conveniently, we can. Now, sometimes you get lucky, right? But lambda is a factor that multiplies out to give 1. So that right there shows lambda couldn't possibly be 0. So you do that first. Then you can cancel the lambdas and conclude this. And it's kind of all downhill from here. When you solve that, you can then plug into this equation to get this monster, which is just a single variable monster, and it's not even that bad of a monster. It's just a quadratic, and you solve, and once you have the z, you plug in to find the x's and y's, and that gives you your critical points. Everybody see the process? Okay. All right. So that's the big idea. The last two examples Again, they're examples. They're pretty readable. They're also discussed in detail if you want to see a detailed discussion in those videos that I referred to in the email that I sent whenever that was. I want to say yesterday, but it might have been Saturday. I forgot. But anyway, if you want to see those details, they are there, and I encourage you to do read through. There again are some little sticky wicket issues with whether things are or are not zero that can actually matter. There's another little sticky wicket here where it's tempting to ignore cases, but you can't just assume that you can solve sometimes for things you'd like to solve for, because you might have to divide. And again, when you divide, you might be dividing by zero. So again, be careful with the cases. And again, these are discussed in detail in those videos. And that does it. So we're done with Math 219. So we got a few minutes left. I'm going to ask you all to, per the request of the university, if you can pull out your phones or laptops and spend the next couple of minutes here on course evals, and I'll be here for office hours at your leisure. So y'all have a good rest of your day.